I'm going to begin by proving a couple of properties of equilateral triangles. The first one is Viviani's theorem. That's that if you have a point inside of an equilateral triangle and you drop perpendiculars to the three sides, the sum of these three lengths is equal to the height of the equilateral triangle. The second property is that these altitudes divide each of the three sides into two segments. These alternating segments, the sum of their lengths is equal to half the perimeter of the equilateral triangle. To skip these and go straight to the problem solution, look for a link in the video description. We'll start with Viviani's. I've divided our equilateral triangle ABC into three triangles with these orange segments PA, PB, and PC. So the area of our triangle can be expressed as a sum of the area of these three smaller triangles. In terms of S, the area of an equilateral triangle is S squared root 3 over 4. And in terms of these three smaller triangles, we have 1/2 base times height, where the base of our three triangles are all S and the heights are X, Y, and Z. Multiplying by 2 and dividing by S, we can solve for x plus y plus z, which is s root 3 over 2, which is also the height of our equilateral triangle. Let's see what happens when we add up the alternating segments on the three sides of our equilateral triangle. We're going to prove that the lengths of these alternating segments is equal to half the perimeter of the equilateral triangle. Before we begin, I just want to quickly write up a formula for the height of a 30, 60, 90 triangle to its hypotenuse. Here are the ratios of the three sides, and I'm going to find h in terms of x. The area of our triangle is x squared root 3 over 2, which is 1/2 base times height, where the base is the hypotenuse. Solving for h, that's x root 3 over 2. We're going to use this formula a lot in our proof. I'm going to begin by drawing a line through this point P. I'm going to call this segment ST. It's going to be parallel to this third side BC. Then I'm going to drop a perpendicular from A down to ST. I'm going to call this point Q. The perpendicular from P that meets side AB, I'm going to call this point X. And I'm going to draw a perpendicular from X to AQ. And I'm going to call this point here U. Now I'm going to find this distance from A to Q in two ways. First, let's find the distance from A to U. AU is the leg of a 30, 60, 90 triangle. That triangle is AXU, and it has a hypotenuse of length C, which means AU is C root 3 over 2. The distance from U to Q is the same as the height of this triangle, SXP. Let's call the distance from P to X, let's call it lowercase x. This is the long leg of a 30, 60, 90 triangle. The shorter leg, SX, has length x over the square root of 3. We'll use our formula here to find the height of this triangle to the hypotenuse, SP. It's the length of the shorter leg multiplied by root 3 over 2. So we're going to take the length of our shorter leg, x over the square root of 3, multiply that by root 3 over 2. So the distance from U to Q is x over 2. And the distance from A to Q is C root 3 over 2 plus x over 2. Now we're going to find the distance from A to Q in a different way. We'll let y be the intersection of the altitude from P to side AC, and we'll let py be equal to lowercase y. I'm going to draw another perpendicular from y to AQ. Let's call this point R. So now we're going to find the distance from A to Q as AR plus RQ. We have triangle ARY, which is also a 30, 60, 90 triangle with hypotenuse length S minus B. This means this longer leg AR is S minus B times the square root of 3 over 2. RQ is the height of this other 30, 60, 90 triangle, triangle PYT. This longer leg, PY, has length Y. The shorter length is Y over the square root of 3. So the height is just the length of the shorter leg times the square root of 3 over 2. This is Y over 2, which is the same thing as RQ. So we have AQ is also S minus B root 3 over 2 plus Y over 2. Now we have two expressions for the distance from A to Q. I'll set them equal to each other, and I'll multiply both sides by 2. Let's replicate this equation for all three sides. We can do this quickly by carefully rotating our vertices and looking for the corresponding side lengths. Ultimately, it doesn't matter if you get the terms wrong, as long as you get all the lengths, because we're just going to add the three of these together. So adding these three equations on the left-hand side, we have the sum of the alternating segments times the square root of 3, plus the lengths of these altitudes. On the right-hand side, when we add these, we're going to have 3s, and then we're going to subtract a, b, and c, and all of this is multiplied by the square root of 3. And then we have our three altitudes again. We can subtract these from both sides and divide these other terms by root 3. We have a plus b plus c on the left and 3s minus a plus b plus c. Solving for a plus b plus c, we get 3/2 s, which is 1/2 of the perimeter of an equilateral triangle. There's one more algebraic property that I'm going to be using, which is that if we have two equivalent fractions and we add their numerators and their denominators, we get one of the fractions that we started with. Now let's return to the problem. First, I'm going to draw perpendiculars from our point P to our three sides. We'll call these points x, y, and z. And by Viviani's, we have the sum of these lengths is equal to the height of our equilateral triangle. The side length of this is 55, so the height is 55 root 3 over 2. We also have that the lengths of these alternating segments from a to x, b to z, and c to y, this is equal to half of the perimeter of the equilateral triangle. Our perimeter is 3 times 55, so the sum of these three lengths is 165 over 2. Now I'm going to draw in these three congruent angles. That's PD, PE, and PF. And we have these lengths. Since we want to find the tangent of these red angles, we can consider using these three right triangles. Let's see if we can find DZ. This is the distance from vertex B to Z minus the distance from B to D. This is BZ minus 7. EY is CY minus 30. Fx is AF minus 40. When we add these three equations together, we get AX, CY, and BZ again, minus 77. We have this expression already. This is equal to 165 over 2. And when we subtract 77, we get 11/2. Since these angles are all congruent, the tangent of the angle that we're interested in is going to be the same as the tangent of the other two congruent angles, BFP and CDP. Using the right triangle ratios from triangle PY triangle FXP, and triangle PDZ. These are three equivalent fractions, so if we add the numerators and denominators, we get the same equivalent fraction. We have these expressions for the numerator and denominator. Here's the numerator, 55 root 3 over 2, and our denominator is 11/2. So this is 5 root 3 and the tangent of our angle. Finally, the problem asks for the square of that tangent, and our answer is 75. If you'd like me to solve any other math contest problems, please leave them in the comments.